Hi everyone, it's Rohan this side, and I welcome you to another video by Lemniscates Academy, where I'm continuing solving the whole paper step by step. And in this video, I'm targeting paper 5 that came in physics in the Cambridge examination during October-November 2024 session. The subject code is 9702 for A-level physics in Cambridge, paper 5, variant 2. Now in the description of this video, you can find the timestamps of different parts of these questions in paper 5. And you can also find the PDF of this paper over there in case if you want to access that. On top of that, I've also provided the links of the WhatsApp groups which you can join and you can ask all the kind of doubts, not with respect to this paper. For this paper, you can obviously comment it in this video so that I get more reach. But yeah, if you want to solve any kind of generic doubts, if you want some kind of help, you can always join our WhatsApp groups. Now, along with that, if you're someone who is looking for a personal coaching where you want to join my online live batches, in that case, you can contact me on this number on the WhatsApp and I'll provide you all the respective details that you need to know. So let's get started with our first question. Figure 1.1 shows a coil made from resistance wire. The coil is placed in cooking oil of mass m. So we are having a cooking oil whose mass we need to first of all measure, and that mass will be m. Inside of this oil, we are going to place this resistance wire. The total length of this resistance wire inside of the oil is given by the letter L. It is the total length of the resistance wire that is inside of the oil. So we're not going to count anything outside of the oil, but within the oil, whatever is the length, we are going to mark it as letter L. Now, a potential difference V is applied to the coil, due to which the temperature of the oil increases by by delta theta. So we're having a potential difference V that is applied to the coil, because of which it's going to produce the heating effect, which is going to make the oil increase its temperature from its initial value. So that is the value of the change in temperature that we're going to measure, given by delta theta, in a specific time interval t. It is suggested that this delta theta is related to L by the relationship that is given by this equation. So how, by changing the value of the length of the wire that is placed inside of the oil, we can see the difference in delta theta. And that is the kind of experiment that we have to perform. And over here, we are already aware about what is M, what is delta theta, what is L, and what is the potential difference, and the time in which you are performing this experiment. The things that we are not aware about for now is the value of A, K, and Z. It is given in the next line that A is the cross-sectional area of the wire. So now we are also aware about what is A. The K and Z are constant. So K and Z are the unknown values which we'll have to figure out based on our experiments. So that is how everything of this equation is now clear to us. Everything that is involved in this equation is, all the information is provided over here itself. So A is the cross-sectional area, K and Z are constants. So based on this, we have to plan a laboratory experiment to test the relationship between this delta theta and L. We have to draw a diagram showing the arrangement of your equipment. So this is a very important thing, drawing a labeled diagram. Then we have to explain how we can get the values of K and Z based on the description or the procedure that we're going to give for the experiment. And in your plan, we should include the following steps: the procedure to be followed, the measurements to be taken of all the things we have mentioned over here, what are the things we need to make sure that it's going to be constant throughout the experiment. Then the analysis of data is basically how we can use the experiment to determine the values of K and Z, and whatever safety precautions that we need to take to carry forward this whole experiment. So this type of questions are pretty simple if you understand the problem statement in your mind. Try to form a basic understanding of, like, if you had to perform this completely by yourself, and if you had to instruct your younger one, basically, let's say your juniors, how would you instruct them? Based on that, you start writing your points. Okay. So the first thing I'm going to do is I'm going to show you all the diagrams that are required for this experiment. And after that, I'll write the whole answer and I will go through it so that you are able to plan it accordingly. So after carefully reading the requirements of our question, you can see that I have done a multiple markings just to see about how we can go ahead and measure these different things. And based on this, we can come up with the diagrams that is required for this experiment. And always in your first question of paper 5, there will be an empty space where you are ideally going to draw the main experiment. And then if you're having good enough time left with you for question 1, you can draw multiple diagrams as you can see in my screen. For now, I have done this extra diagram just so that you can understand different parts required for this experiment. But yes, I always recommend to my students to draw multiple diagrams so that writing about that becomes pretty easy after that. Okay, because in question 1 there is some specific style you need to follow to answer the question so that you can score maximum amount of marks. Okay, and for that it is always recommended that you can draw as many things as possible, even if you're not marking it on the main diagram, at least you are able to visualize it in your head. Okay, because ideally in your examination the main labeled experiment is what they require. All these kind of diagrams are just for you to understand the experiment even clearly. Okay, so just keep that in mind. If you are having good enough time left with you, you can draw multiple diagrams that is neatly labeled. If you're having less amount of time left in your hand, then drawing the main experiment and labeling major components is going to be more than enough. Okay. But now, how do you draw this kind of diagrams? Well, for that, you first need to answer the following questions. Okay. The first thing would be, in this experiment, what is your independent variable? Then, what is your dependent variable? And always in your question one, you are trying to define the relationship between your independent and dependent variable, such that when you're going to change the value of the independent variable, how is it going to affect your dependent variable? Okay, so it is always about the dependent and the independent variables. So in this case, if I talk about the independent variable, it will be the value of L. And because in the question itself, we are asked to determine the relationship between delta theta and L, you can see that L is the only thing that I can change based on which I can measure the value of delta theta. And that is why in our experiment, the independent variable is going to become the length of the resistance wire that is going to be inside of the oil. So what is your dependent variable? My dependent variable is the increase in the value of temperature from the base reading of the temperature of the oil, only dependent on the length L. Everything else in the equation must be constant. So the constants that I'm going to have for this experiment will be the cross-sectional area, the time for which one experiment will be carried forward. So for one value of L, you got a respective value of delta theta. So what was the time taken for that experiment? The same time must be carried forward for different values of L for which you need to find the value of delta theta. So even the value of time per experiment should be held constant. Then the value of the potential difference across the coil. So that can be held constant with the help of a variable resistor. If you are seeing any kind of fluctuations in the value of your voltmeter, you can adjust the settings of the variable resistor so that you can have constant potential difference applied across the wire. So that is how you can have V to be constant. After that, you are having the value of the mass of the cooking oil. So even that needs to be constant. So every time you are going to perform the experiment for different values of L to get the value of delta theta, you are always going to ensure that the mass of the cooking oil remains constant, for which you can use digital balance, and before the experiment, just have the measure of the mass. If there is a little change in the value of M, you will have M as your variable in this equation, not the constant. Okay. And because you are having some kind of heat, if there is any kind of chance of heat loss in your experiment, then you will see the value of M will be less as compared to your previous experiment. So always make sure that the value of mass of the cooking oil remains constant. After that, K is a constant. So let's forget about that. Delta theta we have already mentioned over here, and Z is also constant. So with respect to this equation, these are the things that I have identified initially, that I need to have the length of the wire that's going to placed inside of the cooking oil. Then based on that, for a specific time interval, I'm going to run my experiment where I'm going to connect my power supply to the coil. And then after certain minutes, I'm going to read the value of the change in temperature by keeping all the other variables, or I should say by keeping all the other things constant. Now, based on this, I can come up with some ideas of the diagram. Okay. So in my main experiment, what I have done is I am having a surface. Okay. On a surface, I'm having a wooden board, which is going to work like an insulator. Okay. So that there is no heat that is transferred between the beaker and the wooden board. Okay. So it's just to effectively use our whole workflow of the experiment, because your beaker is already obviously made up of a glass. It's still fine, but yeah, just to have a what do you call this? A precaution. I'm just having a wooden board that is kept over here. On the wooden board, I am having a beaker. Instead of the beaker, I am having a oil, the cooking oil. Okay, and in the cooking oil, I'm going to immerse the resistance wire and the coil, as you can see over here. And you can see that between point A and point B, I am having the length of the wire that is inside of the oil. The remaining part of the wire is outside of the oil. So the value of L will be measured in between A to B. Okay. Then the top of the beaker is covered with the wooden block. Again, this is going to work like an insulin over here, or the insulator over here, where I am having this kind of empty spaces that I have drawn. Basically, you can drill this kind of part from the wooden block where you can insert your thermometer, and you can also have your stirrer stick to continuously, like, just stir through the oil, so that there is a evenly distribution of heat across the every part of the cooking oil, and it's not just sticking towards one side. So continuously stirring of this oil is required to make sure that everywhere the temperature is evenly distributed. All right. So for that also I'm having this empty space that I've drawn. All right. So yes, I'm having a wooden block or the wooden board on which I'm having the beaker, where I've filled it with oil, and I've covered the top part of the beaker with the wooden block, which is having two gaps, one to pass the thermometer and other to pass the stirrer stick. And both of them, let's say for example, if there might be some kind of a way through which heat can escape through this oil, I am having a clay to stop that thing, so that I am utilizing every heat that is produced because of the coil, and because of which I'm having the change in temperature. Okay, so it is very mandatory to stop any heat exchange. And in the first place, that is the reason why I used wooden board at the bottom and also the wooden block at the top. Okay, so clay is going to make sure that there is no heat loss from the beaker to the outside of the experiment. And based on that, we're going to have accurate values of delta theta. Okay, and after that, you can see that stirrer stick is placed inside of this oil. There is a thermometer that is placed inside the oil. Let's say, for example, if you are worried about if it's going to move a lot, in that case, you can have a clamp stand over here. But in my case, I'm having it very much fixed over here. The way that I'm going to have my wooden board will be in such a way that it is able to hold the thermometer. And clay is just going to make sure it is staying in a proper place. All right. And as you can see that over here, I'm getting my wires of the resistance wire over here coming out from the beaker. And even over there, I'm going to have my clay. So that because of the wire coming outside of the beaker, there is no place of for heat to escape this experiment. All right. So even clay is put in over there. And this whole wire is connected to the power supply, to which we are also having the variable resistor. So that, let's say, because of the heating of the wire, if we are having some kind of change in the voltmeter that is applied across the coil, as you can see, right, there are two wires, and parallelly I'm having the voltmeter attached over here, so that if there is any deflection in the value of the voltmeter, I can adjust my variable resistor so that I am having the constant value of the voltmeter as required in the experiment. As you can see, I've mentioned my A to be constant. Sorry, the V to be constant. So that is the setup of the circuit. And I've also drawn a stopwatch over here, so that whenever we are going to give or connect the whole circuit with the power supply, we are going to start the timer. And for a fixed time interval, let's say for example 5 minutes, I'm going to carry this whole experiment for different values of L that is in between A to B. And for different values of L, I'm going to note the value of delta theta. And that is how I'm going to perform the whole experiment. Okay. And to measure different parts of the experiment, major parts of the experiment, I'm going to use diagram 2, 3, and 4 so to explain it even much more better way. So to measure the length in between point A to point B, what I'm going to do is I'm going to first of all straighten up the coil or the resistance wire. Okay, I'm going to uncoil it. I'm going to straighten it up. I'm going to mark two different points, which is going to be within the oil. So in between A to B, my wire is going to be inside of the oil. And after that, I can have the coil pattern over here that will be shown over here as displayed in the diagram. Okay. So yeah, that is how you're going to measure the length of the resistance wire with the help of a meter rule. Then to measure the value of A, okay, to measure the value of A, that is the cross-sectional area, I'm going to use micrometer screw gauge. For that, I have drawn the experiment where I am having the wire over here, and at different position of the wire, I am going to measure the diameter. And after that, I'm going to take the average of that to get the accurate value of the diameter for the wire. So that is about how we can measure the value of A. And every time I'm going to use the same wire so that the area remains unchanged. And I've also talked about T, that every time, let's say for example, for different values of L, I'm going to carry forward this experiment for a fixed time interval, that is 5 minutes, for example. And how can we keep the value of mass constant for the cooking oil? I even talked about that every time before you start the experiment for different values of L, you have your digital uh, meter ready on which you are placing your beaker and then setting the value of the digital balance to 0 gram with the beaker itself. And then after that, you pour the oil inside that beaker so that the mass that you're going to get over here will be just with respect to that oil. So let's say, for example, in the first experiment, you are using some 20 grams of oil or 20, whatever is the reading that you're coming up with. Okay, whatever is the reading, you get the value of the mass, and that same value of mass you will ensure after every value of L you are changing. You first make sure that the oil mass is constant. If not, you need to just put some more oil so that the value of mass is constant. That is how you can keep M constant. Okay. And then to ensure that there is no heat loss, I have already mentioned that you're going to have a wooden block. And because you have drawn multiple holes in there to pour the thermometer and the stirrer stick, you're going to insulate it completely with the help of this clay, wherever you think there could be an opening from where the heat loss can be there. And also make sure to perform the whole experiment on same time. Let's say, for example, it shouldn't be like we are performing half of the experiment in the morning and half of the experiment in the evening time, because the room temperature will be changing on different parts of the day. And therefore, always make sure the initial value of the temperature is same for all the experiments so that measuring the delta theta becomes pretty simple. Okay. And yeah, and just to make sure that the temperature is evenly distributed throughout the oil, make sure to use your stirrer stick that I've already explained about. So that is the whole idea that I've given to you about how you can carry forward with your experiment. Now, based on this, if I talk about some safety precautions, it could be with respect to, let's say, while steering the stick, just make sure that the whole experiment does not get affected. Everything else should remain same. So draw a careful hole over here so that you are having the liberty to move the steer stick here and there. Okay, and the clay should not be very much tight for it to not be stirred properly. All right. And the second thing should be you should be using, let's say, a low value of the voltage, somewhere like less than 12 voltage, to effectively uh, be cautious about, anything with respect to the electricity that is going on around the oil. Okay, because you might get some kind of shock because of that. Always use some kind of gloves, right? So all these kind of points are for the safety precautions. And then after this, what you're going to do is you're going to repeat the experiment for the same value of L for 3 times. And after that, you're going to take the average value of the delta theta in all of the 3 experiments so that you are getting a proper value of delta theta. And like this, you can carry forward the multiple experiments. And for, let's say, 6 different readings, you can go ahead and plot the graph. And based on that, you're going to see a clear relationship, like a straight line graph between the delta theta and L. And based on that, you're going to identify how to measure K and Z. So a lot of talking, but I hope that the idea is pretty clear to you now. Now let's go ahead and write out the points about how we can go ahead and get all the things that I've just mentioned over here into the paper. So all the points that I just explained, I have converted that into the paragraph format over here. You can go ahead and write it in the pointwise format as well to save the time, but in this case, I am sticking with the paragraph format. So to start with, we are having the experimental setup and the procedure. We begin by measuring the mass of the cooking oil, as keeping it constant is very crucial for fair testing of the experiment. Using a digital balance, we first set a zero reading with beaker on top, as I have shown in my first part of my diagram 4. Then we pour the cooking oil into the beaker and note the value of the mass M. So that is shown over here in the second part of the diagram 4. And that mass of the oil must be constant throughout the experiments that we will be performing for this particular question. So to ensure the consistency in every trial, we use the same beaker and measure the same oil mass before each experiment. And yes, as mentioned, this is given in step or diagram 4. Okay. Next, we prepare the resistance wire that will be submerged in the oil. And for this, we need to calculate the length of the wire that will be inside the oil. So since directly measuring a coiled wire in the beaker is challenging due to its shape, we first straighten the wire and use meter rule to accurately measure and cut different lengths from A to B before forming the coil as shown in diagram 2. So we can get multiple value of the lengths. We can cut it from the whole wire for different values of L. And from point A to B, I'm going to make sure only that part is submerged in the oil, and the remaining part is outside of the oil connected to the variable resistor and the power supply. So this value of A to B I can measure over here and cut out multiple lengths for which I can get different values of respective delta theta. And that point has been mentioned over here. And this way we ensure that the length L submerged in the oil is precisely controlled, because we are able to see that A and B, anything below that is inside the oil and anything above that is outside the oil. The wire is then coiled uniformly to maintain consistent heat distribution throughout the oil. So we then we basically coil the wire uniformly to maintain that consistent heat distribution within the cooking oil. So once we are done with the value of L, next let's focus on the value of the cross-sectional area. So to measure the cross-sectional area, we first determine the diameter D of the wire using a micrometer screw gauge as shown in diagram 3. So this diagram is useful to calculate the value of the diameter of the wire. And it's mentioned that since the diagram or the diameter may vary slightly along the length of the wire, we take multiple readings at different points and calculate average diameter for better accuracy. So throughout the wire, we are going to measure different values of the diameter and then take the average of it to get better, or I should say accurate value of the diameter. Then once we are having the diameter of that wire, the cross-sectional part of the wire is a circle. So the area of circle is given as pi d square by 4 or pi r square. From the diameter, you can calculate the radius also, or directly you can plug it into this pi d square by 4 to get the value of area. And then once the area is calculated, we go ahead and set up the electrical circuit. So far, what have we done? We have first calculated the value of mass of the oil. Then we measured the length of the wire that will be submerged in the oil. Then we calculated the diameter, and based on the diameter, we calculated the cross-sectional area of the wire. Now we are going to set up the electrical circuit. The coil is fully submerged in the oil inside the beaker, which is placed on an insulating surface, that is the wooden board, as you can see in the diagram. And that is going to just make sure that there is no heat flow from the beaker towards the any kind of surface that you're using. The power supply is connected to the wire with a voltmeter in parallel to measure the potential difference across the wire. And a variable resistor is included to adjust and maintain a fixed voltage V that you can see in the voltmeter over here. So we are talking now about how this coil is connected to the power supply, and then how we are having the variable resistor to maintain the value of potential difference across the wire. That is how we can have the constant value of V. And then after that, before switching on the power, we first record the initial temperature theta 0 using a thermometer placed inside the oil. To ensure that heat is evenly distributed, we gently stir the oil with a stirrer stick that we have added into the experiment, and being careful about not spilling any liquid over here and there. We then switch on the power supply and start the stopwatch simultaneously. So once we are starting this steering of this cooking oil and we connect the power to the circuit, at the same time we are going to start the stopwatch. So that part is explained over here so far. The wire begins to hit the oil, and after a fixed time, let's say for example 5 minutes, we record the final temperature and then calculate that final temperature using delta, or I should say theta f. And then calculating the rise in the temperature, that is delta theta, we measure it by delta f by minus delta 0. So if you get the final temperature minus the initial temperature, that is how you're going to get the temperature rise of the cooking oil. Now throughout the experiment, ensure that beaker is placed on the wooden board, and the top part is also covered with a wooden block to ensure no heat loss or minimum heat loss in the experiment. Near the wire entering the beaker, thermometer and the statistic, make sure to place clay for preventing any additional heat losses due to our experimental setup. So you can see that on the wooden block, I have drawn multiple different parts to enter the statistic and the thermometer. And even over here, as we are passing the wire, I am placing clay to avoid any additional heat loss in the system. And then to investigate how delta theta depends on L, so I'm mentioning that L is my independent variable, delta theta is my dependent variable on L. We repeat the experiment with different pre-measured lengths of L that is going to be submerged inside of the coil. So I'm talking about different A to B lengths that we have cut out. To repeat this experiment for different L, we can measure different values of delta theta. And we are going to mention that while getting the relationship between the L and delta theta, we are ensuring that all the other variables remain unchanged. That is the mass of the oil, the potential difference across the wire, the cross-sectional area of the wire, and the time of hitting for each value of L. Each experiment for the same value of length is repeated 3 times, and an average value of delta theta is taken to improve the accuracy of the experiment. So that was about how we can take the experimental setup and the procedure about that experiment. Next up is the data analysis, that how we can perform the data analysis so that we can find the value of the unknown constants, that is k and z. So once data is collected, we analyze it by plotting a graph of delta theta on the y-axis, that is the dependent variable, and the independent variable L. So because we are planning to get a straight line, I'm going to get 1 by L on the x-axis. Okay, I'll just mention over here x-axis. So rearranging this equation in the format of a straight line, I'm going to get, so initially this was the equation that is given to us. What I've done, I made mk delta theta the subject and placed z on the other side. So that is the equation that I'm going to get. And if you can notice, I'm getting 1 by L over here along with the ATV square. Now, because I want to plot delta theta on the y-axis, it is must that I can send my mk on the other side. So I'm going to divide mk on both the sides, and because of which mk on the left side is completely eliminated. On the right hand side for the first term, I'm going to get ATV square by mk, that is multiplied with 1 by L, and then minus z by mk. I'm also dividing the second term with mk, and that is how I'm going to get the equation in the format of a straight line, where on the y-axis I'm having delta theta. On the x-axis, because of this relationship, I'm going to plot 1 by L, so that the gradient is equal to ATV square by mk as written over here. And by using that gradient, I can find the value of k by making that the subject of formula. And similarly, by using the y-intercept of minus z by mk, I can make z the subject of formula to find out the value of z using y-intercept. So that is how we perform the data analysis based on the experiment that we have performed. And at the end, I'm just going to have the safety considerations. That is, use low voltage below 12 voltage. I had already explained about this previously, to avoid excessive hitting of the wire. Because if you hit it excessively, then the changes in the voltage will be pretty much evident. And therefore, using a low voltage is an ideal scenario. The hot oil is handled carefully using heat-proof gloves to prevent any burns onto your skin. Then the electrical connections are properly checked for safety and to avoid any kind of short circuits. The beaker is kept stable on the wooden board to avoid any kind of spillage. Once it is stable, then we start the experiment. So based on this is how we have designed the experiment. Okay, the way of writing this will always be different for different people. There is no problem. If you're mentioning about all the points, then scoring full marks for question one becomes pretty easy. Okay, so just to make sure, what have we done for question one? The procedure and the experiments to be taken, we are done with that. We know what is independent variable, dependent variable, and the control of the variables, then how we can measure different parts, and from the analysis of data, how we can find out the value of k and z, and what are the safety precautions. So ensuring all the parts are covered, I am pretty much sure that going through this kind of setup can guarantee a full mark for the question one of this paper. Now for question two, it is given that a student investigates the refraction of a white light entering a transparent rectangular block. A narrow beam of light enters the block at the midpoint of one of the shorter sides, as you can see over here in the diagram. The angle of incidence, that is theta, is measured as shown in figure 2.1, which is not to scale. The distance d between the corner of the block and the point where the beam of the light touches the boundary of the block is measured. So this is the d that we are talking about. The experiment is repeated for different values of delta theta, or I should say theta. I messed up from the previous question. It should not be delta theta, it is theta in this case. It is suggested that d and theta are related by this particular equation, where b and n are constants. In part A, a graph is plotted of d square on the y-axis against 1 by sine square theta on the x-axis. Determine the expression for the gradient and y-intercept. So let's see how we can perform this. It's just a manipulation of this given equation to get this final answer. So for this, what I'm going to do is I'm going to make sure that whatever I'm going to plot on y-axis is the subject of formula. So for that, I'm going to multiply my b plus d square on the right hand side and keep my n square on the left hand side. So this is going to make bn square is equal to sine square theta into b, sine square theta into b plus d square sine square theta. And then because I want to make d square the subject of formula, what I'll do is, first of all, from here, I'll make sine square theta as the common factor. Okay, so it's going to be sine square theta, and then in the bracket, I am having b plus d square. Initially, I guess if I have done that, it would have saved my time. But anyways, now that we have done this, now what I'm going to do is I'm going to divide my sine square theta on both the sides. So it's going to become b plus d square is equal to bn square divided by sine square theta, but I'll just write over here like 1 by sine square theta, because I'm going to plot by 1 by sine square theta on the x-axis. So potentially this is going to become our gradient, and therefore I can say that my d square is equal to bn square into 1 by sine square theta minus b. So my gradient over here is going to become bn square, and my y-intercept is going to become minus b. And now for part b, we are having the values of theta, 1 by sine square theta, and d. And d is given in centimeters. And if you notice, even the absolute uncertainties for the d is provided to us. So based on this, we have to calculate and record the values of d square in centimeters squared in the given table. And along with that, we also need to include the absolute uncertainties in d square. So I'll talk about the absolute uncertainties in a while. Let us first calculate the values of d square and record it in the table. Just note that because we are dealing with the least significant figures being 1 SF, I'm going to fill up my answers of d square, including the values of the uncertainties or absolute uncertainties, correct to one significant figure as well, according to the rules of the marking scheme of physics. So in this case, what I'll do is I'll first of all grab my calci and first just get the square of the d. So 24.8 square, and correct to 1 SF, it is going to become 615. So now that I'm done filling the values of d square correct to 1 SF, now it's time to measure the value of the absolute uncertainties in D square. And for that, first of all, I'll just take away my calci and give you a formula through which you can calculate the value of D square very quickly. So I know that because I'm having the value of absolute uncertainty in D, I can directly use that to calculate the absolute uncertainty in D square. So just make sure you are simply not doing 2 into delta D being the absolute uncertainty in D square. Because we are dealing with a multiplication of D, that is D into D, that is what is D square, we need to deal with the percentage uncertainties, okay? If you're dealing with, let's say, D plus D, in that case, you can go with the direct manipulations of the absolute uncertainty without involving percentage uncertainties. But whenever you're dealing with multiplications, just make sure to use that multiplication rules of percentage uncertainty. So in this case, in order to get the percentage uncertainty of D square, I'll need to get 2 times the percentage uncertainty in D. And then delta D square over D square into 100 on both the sides will be cancelling out. So 2 times delta D by D. And then if I want to make delta D square the subject, I'll be having 2 times delta D by D into D square. So one of the D's from the top and the bottom gets cancelled out. So delta D square is equal to 2 delta D into D. And if you notice throughout the whole calculations for delta D, the value is constant, that is 0.2. So 2 into 0.2 is becoming 0.4. So 0.4 D, where D is the value of the D over here. And if I just substitute the value of this D into this equation, 0.4 into that value of D, I'll get the absolute uncertainty of D square. And correct to one SF, I'll just fill it up over here. So to start with this calculations, I'll again take my calci and do 24.8 into 0.4. And the value comes out to be 9.92, which correct to one SF, if you notice, it is going to be 10. So I'll fill up 10. And then just repeat all of the steps, 0.4 into this value of D to get the delta D square for this row. Similarly, I'll carry forward with the other values as well. Alright guys, so that is how we fill up the values of the absolute uncertainty in D square. In case of any kind of more doubts for this particular part, please make sure to mention them in the comments and I'll get back to you as soon as possible. Alright guys, so now that we are done with the tabular part, all the remaining questions are based on how well you are able to plot the graph in between 1 by sin square theta on your x-axis and d square on your y-axis, including the error bars for your d square. The more accurate the graph will be, more accurate your answers for the following parts will become. Okay, and let's say for example, if your graph is not that accurate, you're not able to get your line of best fit or worst fit properly set on the graph. If there are errors over there, then the inaccuracies for the following parts will become very high. Okay, so please make sure you are taking around 5 to 10 minutes of time just plotting the graph in a proper way, including the line of best fit and the worst fit. And within 10 minutes, once you are done with this, then calculating the following parts becomes pretty simple. Okay. And for just like, not taking your good time because I'm working on my laptop right now, I'm not working on my iPad. So it's going to take a lot of time for me to do it. So I've already filled the remaining part of this paper over here and I'll just go through it because as I mentioned, all the questions in question all the parts in the question 2 of paper 5 are 99% similar, right? The 1% thing that is not similar is the last question because last question depends on the scenario that is given to you in your question 2 based on this equation. So apart from that, all the other questions you will see in paper 5 question 2 will be exactly same. For example, calculate the gradient and the absolute uncertainty in the gradient. That will be about the y-intercept. Then based on the relationship that you had used in your previous part, using gradient and y-intercept, calculate the values of b and n respectively. Right. So this type of questions are exactly same. Okay, so I'll just go through what I've done over here so that it's not taking a lot of your time. If I talk about like how much amount of time I had gone through to get my plot on the laptop, it was pretty difficult because it is very much like it's very very difficult to get my drawing with the straight line without the scale, zooming in, zooming out. So it was taking me around 15 to 20 minutes to get it done, and that is why I am just going through it very quickly for you. Okay. So the first thing you need to do to plot the graph between d square on y-axis and 1 by sine square on x-axis, including the error bars for d square, would be just get your x-axis coordinate and the y-axis coordinate and simply plot it. And the way that you're going to plot it is just going to have this kind of a cross that is covered with a circle. That is how you're going to mark it. Within one small square, you need to mark this kind of mark for this x and y coordinates for one single point. And then for the y-axis values, you're also going to have an error bar that is going to be similar to what you are seeing on the screen currently. Now, keeping these ideas, let's see how the first coordinate is going to be plotted. You can follow with the remaining coordinates and get your first part of C done. Okay. So on x-axis, it is 4.39. On y-axis, it is 615 with plus minus 10 uncertainty. So on the x-axis, where is 4.39? If you can see that there is 0.5 values that I need to cover in 10 boxes. So in one boxes, I'm having a value of 0.05. So over here it is 1, then this is going to become 1.05, this is 1.1, and 1.15, 1.2, 1.25, 1.3, so on and so forth. So where could be 4.39? I am looking forward to 4.39. So over here, this is 4, then this will be 4.05, 4.1, 4.15, 4.2, 4.25, 4.3, 4.35, and 4.4. So just to the left of 4.4, we'll be having 4.39. And then I need to plot over here the value on the y-axis as 615. So if you see over here, in this 10 boxes, I need to fit 50 values. So 50 by 10 is 5. So each box is having a value of 5. So where could be 615? This is 605, this is 610, this is 615. So over here, that is the reason why I have plotted. My x-axis value is 4.39, my y-axis value is 615. And yeah, within this one square, I have got my circle and the cross done. Now, what is the, that is how basically I marked the point. Now I have yet not covered the uncertainty part. So that is going to include this error bar 10 units above this point and 10 units below this point. And I'm dealing with my y-axis because d square is plotted on y-axis, not x-axis. So 615 plus 10 will be 625. So it goes over here. 615 minus 10 will be 605. So it goes over here. And that is how you draw the error bar with the uncertainty of 10 for this graph. Similarly, you can repeat for all the points, and that is how you're going to be done with your C part 1. And after that, you are having C part 2. That is to draw the straight line for the best fit and a worst acceptable straight line on the same graph. We also need to label both the lines. So as you can see that I have drawn two lines, one is a green line, one is a yellow line. In your case, you will be dealing only with pencil. So what you can do is you can have a best fit line that is completely straight line. And for the worst fit line, you can have a broken line, okay, dash line. So in my case, because I'm having access to the colors, I am going to mark it like this. But in your case, I hope you got the point. So now what is the meaning of line of best fit? Line of best fit is that line that passes closely to as many points as possible such that you are getting least amount of error with respect to your points that you've marked on the graph, that is with respect to the circle and the cross. So how far I am from this kind of crosses on with respect to this green line, that is what I need to check. The least amount of error between these points and the line is going to make sure that I am having best fit line that is drawn on the graph. Okay, to make it very simpler for you to understand this, if it is a bit confusing, the line of the best fit can be plotted in a way such that if you calculate the distance of the line for the points that is below the line, that distance should be approximately equal to the distance for the points that is above the line. So for example, if I show you over here, this point is approximately a few units below the green line. this point is approximately the same distance above the green line. So the error with respect to these 2 points for my green line is approximately cancelled out. It's nullified. So for the 2 points, it is really good. Now let's see if I can do it for the other points as well. So this point is slightly above the green line. This point is also slightly more above the green line as compared to the previous point. And for the other 2 points, as you can see that this is far below the green line and this is just on the green line. So approximately these 2 points are nullifying the effect of these 2 points. The distance it was above the line for these 2 points, it's approximately the same distance for these 2 points. So again, the overall error, if you can see over here, is nullified. It means that this is the line of the best fit that I've drawn, which is really very accurate. And how can you confirm it for your case? Let's say if you are drawing this kind of a best fit line, you can check in the marking scheme. In the marking scheme for this paper, it is mentioned that if your line of best fit is passing between 2 points, okay, then you are having an accurate line of best fit for your question. So the first requirement is that when the value of y is 250, your x must be exactly in between 1.9 and 2. So in my case, it is over here. So if I just scroll down, it is 1.95. On the left, I'm having 1.9. On the right, I'm having 2. So my value is exactly in between that. So it is really good. Let's say in your case, your value was 1.925 or maybe 1.975. Even that would be good because in the marking scheme, they mentioned that when the value of y-axis for the line of best fit is 250, on the x-axis, it should be in between this. So if that is good, you are good to go. But this is only 50%. Another 50% in the marking scheme is given to if the value of y is 500. Okay. So for that 500, if I just take a look over here, my value is coming out to be 3.55. In the marking scheme, it is given that your value should be exactly in between 3.55 and 3.65. So anywhere in between that, it is going to be accepted. So because mine is coming out to be 3.65, so this is really good. Okay. So that is how I can guarantee that my line of best fit is accurate. In your case, I hope you got the idea of how you are going to compare. In case if you are having any kind of doubts about this, please mention that in the comment section below. Now for the worst fit line, there are two options. The shallowest line you can draw for the shallowest gradient, or you can draw it for the steepest gradient. Now how you can get the steepest gradient? When you join the line from the top of the error bar for the oops, where is the graph? Just a second. Yeah. So how do you get the steeper line? See, for the steeper line, you need to start from the least value of the first point till the highest value of the last point. That is the steepest curve that you can get for the worst acceptable line. You are within the error bar, but in a way that once you are starting with the first point, you are starting from the minimum error for the first point, and for the last point, you are going till the maximum error. So the steepness is maximum for this. What could be the shallowest possible line? The shallowest line for this would be for the first point, I'm starting from the higher error value, and then I'm ending at the last point, and the least value for that last point is what I'm choosing. So that line will be having a shallow value of the gradient as compared to what I've drawn over here. But either of the cases are accepted. The reason I've gone with the steepest gradient is because when I was trying to draw the shallow gradient, not all the error bars were crossing properly. Okay, I guess this point and this point was not getting properly fit on my graph. And according to the marking scheme, we must pass our best fit and the worst fit line through all the error bars. Not for a single point, my line should not touch the error bars or literally anywhere through the error bars. For each point, my both the lines must pass through all of the error bars. So for the shallowest gradient, my first statement was for the shallowest gradient that I'm going from the starting, I'm going for the high error of the starting point to the least error of the ending point. Okay, so I was missing these 2 points completely. And then when I tried the steepest gradient, in that case, as you can see that all the error bars are completely covered. And that is how I'm going to guarantee that even this is going to be an accurate worst fit line. Now, based on this, you will be having the third part of question C, that is to determine the gradient of the line of the best fit and include the absolute uncertainty in your answer. Again, it is a straightforward question as we have in any other question 2 of paper 5. That is, you calculate the gradient of the best fit line, calculate the gradient of the worst fit line. Then the absolute difference between them will be the value of the absolute uncertainty. So how do you get the how do you calculate the gradient of the best fit and the worst fit line? The only rule you need to follow is that the point that you choose from the graph, it should be such a way that it is covering at least half of the paper. Okay. And with respect to that, if you can see for the line of the best fit, the points that I've chosen are 1.45, 175 and 4.25, 594. So based on that, if I calculate the gradient of the best fit line, I'll be getting 149.6. And with respect to the worst fit line, if I can show it to you, the yellow is the worst fit line as I can see the label. So I'm having 1.5, 175 and 4.25, 595. So using those values, if I plug in into my gradient calculations, I'll be getting 152.7. Now from this, if I just calculate the difference between them and take the absolute value of it, I'm getting the output as 3.1. So my final answer of the uncertainty is having one decimal place. So my final answer for the gradient will also have one decimal place. And therefore, my final answer over here would be 149.6. That is the value of the gradient of the best fit plus minus the absolute uncertainty is always the difference between them. So that is 3.1. Okay. So that is how you're going to perform part 3 of question C. Now, after this, you are asked to calculate the y-intercept and also the absolute uncertainty in this. So we know that y is equal to mx plus c. So if you make c the subject, it will be y minus mx. So to calculate the y-intercept of the best fit line, you are going to do y minus the best fit gradient into x. So from this point, I have taken, I guess, 4.25 and 594. So this is 4.25 and 594 for the best fit. And the gradient value that we had got for the best fit was 149.6. So if I substitute these values into the equation, 594 for the y, 149.6 for the best fit gradient, and 4.25 is the x value, I am ending up my y-intercept as minus 41.8 as the final answer. And for the worst fit y-intercept, I'm doing exactly the same thing, plugging in the values of the worst fit line, and I'm getting the output as minus 54.0, correct to 3SF. And then the sorry, not percentage, but the absolute uncertainty is calculated just like how we had calculated the gradient. That is absolute value of the worst fit minus best fit. In this case, I got 12.2. So because again, I'm having one decimal place followed in the absolute uncertainty, my final answer of the y-intercept will also be with respect to one decimal place. So my final answer of the y-intercept with respect to the best fit is minus 41.8 plus minus the uncertainty value, or I should say absolute uncertainty value of the difference between them, that is 12.2. That is how we are done with the fourth part of question C. Then for the next part, you are asked to utilize the answers of part A and the above two parts to determine the values of B and N. And we have to include appropriate units. So basically they are asking us to utilize the answer from your part A, which is this, that my gradient is equal to bn square and my y-intercept is equal to minus b. And now that we are having the values of the gradient and the y-intercept, we can go ahead and find out the values of b and n respectively. And the way that I'll be doing this over here would be, I know that my y-intercept is equals to negative b. So this implies that my b will be equal to negative y-intercept. So my negative of y-intercept, that is 41.8, will be equal to 41.8. And now because my y-intercept was having the or my y-axis was having the units of centimeter square, my units for the y-intercept or the value of the b will also be centimeter square. Similar to this, to calculate the value of n, the equation that is given to me in part is gradient is equal to bn square, making n the subject I'm having square root of m by b. So the value of m is given to us as 149.6 and the value of b that we got is 41.8. Taking the square root of that, I'm getting 1.89 as the answer. Okay, so this value simplifies to 1.89. And then to take the units, if I do the square root of my gradient divided by the y-intercept, you will see that the gradient value will be y over x. So centimeter square over, this is unitless. So on the top part, you are left with centimeter square with respect to the gradient. And for the y-intercept is also centimeter square. So centimeter square and centimeter square are going to be cancelled out and you are left with no units for n. And these are the values that we'll be getting for b and n. Just make sure that not all of the values are going to be matching, obviously because your graph will be different than mine. So do expect slight amount of variation. If your answer is falling within my values of the uncertainty, that is absolutely correct. You don't need to worry about it. Okay. And then we are having part 2 of question D, that is determine the percentage uncertainty in n. So I know that the value of n I can get with the help of this equation. And if I rearrange this, it's going to become n is equal to square root of m by b. So to calculate the percentage uncertainty in the n, I'll be having half into percentage uncertainty of m plus, because of the square root, half the percentage uncertainty of b. So to calculate this, I can say that half is in common. I'll take half as common factor. Then to calculate the percentage uncertainty of m, it will be delta m by m. So delta m value is 3.1 and the value of m is 149.6. So that is why 3.1 by 149.6 plus the value of b, because it's the, like, the value of b is same as y-intercept as you can see. So on the top I am writing 12.2 because the I guess I've done some kind of an error over here. Just a second. Why did I write? Oh yeah, 12.2 is the y-intercept's uncertainty, right? So yeah, so the value of the b's uncertainty will also be 12.2. So 12.2 divided by the 41.8 is going to give me the percentage uncertainty in b. Both of them are added together, multiplied by half, and to convert it into a percentage uncertainty, I'm going to multiply it with 100. So I'm getting the output of 15.63%, which is rounding off to 16%. So that is how you determine the percentage uncertainty. Again, all of the answers are exactly same like other papers, so I'm just fast forwarding it uh, to this kind of things. Okay, I'm not really discussing about it. In case of having any kind of errors, not understanding what I've done over here, it means that your concepts of the respective topics are very weak. In that case, I'll first recommend you to revise the topics and then get back to this particular video. Okay, or else if you're having any doubts, please make sure to post them in the comment section and I'll get back to you as soon as possible. Now for the last part where we are asked to determine the value of theta when the value of d is given us to 30 centimeters. So from the original equation, if I make theta the subject, I am going to get this formula. Plug in the value of n as what you've got over here, 1.89, the value of b as 41.8 and the value of d as 30. And plugging this into your calc, your output of theta will become 23.5. So if you can notice over here, the value of d is 30. Okay. And in the trend, as you can see that as we go above the table, the value of d is increasing, but then the value of theta is decreasing, right? As the value of d increases, the value of theta is decreasing. And this is followed. If the value of d is going to be 30, then the theta value must be less than 28.5. And I've got 23.5, which makes sense, right? According to what we have got. So every time when you calculate the final answer of the last question of question 2 of paper 5, always try to see if this kind of thing is making sense or not. If it is making sense, then the chances that it is correct is very high. Let's say, for example, I got a value over here of theta as something that is like, let's say 30. So 30 is in between 28.5 and 33.5, which is not making sense because I can see that as the value of d is greater than 30, it must be giving me the value of theta is less than 28.5, not in between this. In that case, my d must be between 21.4 to 24.8 to get the theta value in between that. So yeah, which makes me wonder that I've done something incorrect somewhere. Okay, so I'll just cross check my working and just see what is the error. But in this case, it does not seem like any error. So this must be your final answer. I hope that the question 2 for paper 5 is not that difficult for you guys. In case, let's say for example, if I'm getting comments like, please explain me what is the perfect way to master the question to such that we can solve this whole question within 15 to 20 minutes, then if I'm having, let's say, at least 5 comments, then for sure I'll be creating a separate video where I'll be teaching about how you can do it very effectively. Okay. The reason I went with this very quickly is because I expect you guys to know that this kind of calculations exist for question 2 of paper 5. All right, guys. So that's the end of the video over here. I hope that you were able to understand both the questions properly. If not, please feel free to leave the comments in this video. I'll just go ahead and solve all of your questions as soon as possible. And with these things being said, please make sure to subscribe my channel and also share it with your friends who are appearing for the A-level physics in the upcoming sessions, and it will be helpful for them